All right, so let's talk about how we use significant figures in our everyday chemistry math. Using significant figures is just trying to be aware that measurements always have some degree of imperfection or some degree of error. So when we think of sig figs, significant figures, also known sometimes as significant digits, it's best to kind of think of them as significant place values in the measurement, which place values are important to us. And we're always going to say that a significant figure or measurements are going to contain all place values known for certain, those ones that are marked on the actual measuring device, plus one estimated value. That's that space in between those marks on the measuring device, like a ruler or a graduated cylinder. And then don't forget, like a digital balance is automatically going to have an estimated place value that will be the last place value that happens to be there. So all place values known for certain plus one estimated place value. This is only going to apply to measured numbers, not to counted numbers or constants. Like pi doesn't have sig figs in it, or if we're saying there's 3 test tubes, there's no degree of uncertainty there. It's not a measured value. So we have some rules for sig figs. The easy rule is if you are given a number, you're reading a number that someone else gave you, you are going to count all non-zero numbers as significant. So automatically, if the number is a number 1 through 9, it's going to count. So in this example, 6.56, all of these are non-zeros. There's 3 sig figs. 57 has 2 sig figs, and then here are all non-zero numbers. So there's 4 sig figs in this example. The second rule is what I call the sandwich zero rule. So if you have a 0 in between non-zeros, that 0 is going to count. So 201, there's 3 place values that are significant here. The 2, the 0, the 1, that 0 is sandwiched between 2 non-zeros. An example where you have 2 zeros sandwiched, 5.004, there's 4 significant place values here. And this is trying to show you that you can have multiple zeros as long as there's a non-zero on the left and on the right. So then likewise on this number here, we have 1, 2, 3, 4, 5, 6, because all of these zeros are in between a 4 and a 9. Finally, this is the most complicated rule, but it's really not that complicated if you pay special attention to this word and. Zeros that are to the right hand side, so it has to be on the right. So here's a 0 on the right of a 5, and I see a drawn decimal point. So I see that decimal, that means that this 0 is going to count. So that's 50 with a decimal point. There's 2 sig figs there. This 50 with a decimal point and a 0 to the right, that's going to be 3. 0 and 0 are both on the right hand side of the 5, and I see a drawn decimal point. In this number, I see 2 sig figs, a decimal point. The 1 counts because it's a non-zero. This 0 is on the right-hand side of a non-zero, and I see the drawn decimal point. It will count. These are all going to count because they're non-zeros. This 0 is on the left, so it doesn't meet the first condition. 0 is on the right. But this 0 is on the right, and I see a drawn decimal. So there's 5 sig figs in this number. And the 5, 0, 0, there's 1 sig fig because I don't see a drawn decimal point. Even though these zeros are on the right-hand side, there's no drawn decimal point. Compared to this 5,000, that decimal point makes these ones significant. In all these cases, we're looking at these numbers as if someone else measured some kind of value and we are reading their measurement. And that's how we know how many sig figs we have. So some example problems of this. If I have 9.66, you can underline the place values that are going to count. So the first rule, non-zeros, 1, 2, 3. 3 sig figs. Second problem, a 3 counts automatically. Do I see sandwich zeros? No, but I do see zeros here. All 5 of these zeros are on the right-hand side of 3, and I see a visibly drawn decimal point. So that makes 6 sig figs. The 23,000, the 2 and the 3 automatically count. No sandwich zeros, but there are 3 to the right-hand side of a non-zero, and I see a visibly drawn decimal point. That makes 5. So notice it doesn't matter where that decimal point happens to be, as long as it's in that number and you can visibly see it. So how about rounding with sig figs? When we do math problems, we're going to have to round numbers to a certain number of sig figs, which we'll learn about next. The numbers that are in that math problem are going to determine how many sig figs we have, and based on the math process we're doing. We're almost always going to round like normal, except if there happens to be a lone 5. So if there's a lone 5, after the place value that you're going to retain, you're going to keep that last place value as an even digit. So what that means, in this number, let's say we were going to keep that 7, so we're going to round to the 10th position. The 7 is followed by a 5 and only a 5. So this is an example of a lone 5. This would turn into an 8. We're going to make that even. We're going to round up. In this case, still using the same place value, we're following by a 5, but the 5 has something behind it. So this is not a lone 5. You're going to round normal, make it an 8. Finally, 7 followed by a 5, 0. Again, not a lone 5, because that 0 is attached to the 5. It's not a 5 by itself. This is also going to be 0.8. So in this example, all three of these round to 0.8. This example is showing you how the lone 5 rule gets weird. Not weird, but where we see rounding different than what we would expect. Since this is the place value we're keeping and it's a 6, followed by a 5 all by itself, it's a lone 5. We're going to keep this as 6. This rounds to 0.6. This is not a lone 5. This is not a lone 5. So in this case, this number and this number are both going to round to 0.7. Even though the first and the last are basically the same size and number, the significant figures involved make it a different rounding process. That's the lone 5 rule. A couple examples of this. If we're going to round this first number into 1 sig fig, I'm going to mark the place value I'm going to keep, 1 place value. My 8's followed by a 5 by itself, that's a lone 5. It's going to stay even, it's going to stay an 8. Number 2, I have 3 sig figs, 1, 2, 3. A 1 followed by a 6 turns into a 2. So 8, 1, 2. However, this 2 is in the tens position. I need to keep it in the tens, which means I need to add a 0. I have 3 sig figs here as long as I don't draw a decimal point. With 1 sig fig in this number, I need to do 22 times 10 to the second, so 22 times 100 gives me 2200. But we keep this place value, so that turns into 2000. Or we could also write it as 2 times 10 to the third. And then 4 sig figs, so my fourth one's right there. A 5 followed by a 2 stays a 5, 77.55. That number now has 4 sig figs. So when we do math problems, we have a couple of different rules. Most of the math we do in chemistry is multiplication and division. And that's the easier rule, I would say, to use for sig fig reasons. You're going to count the number of sig figs in each of the numbers that are in your math problem, and whichever number had the fewest number of sig figs, that's the one that you report your answer to. Basically, we're saying we're going to use the weakest measurement as our determining factor for how many place values we can actually report. So if you do this first problem here, the 83.9 times the 0.67 times the 4300, your calculator is going to give you this number, 241715.9. So I'm going to look at each of these and count the number of sig figs. 3 non-zeros, 3 sig figs. 2 non-zeros, these count. The first 0 doesn't count because it's to the left of a non-zero, so that's why it doesn't count. And then this number has 2 non-zeros. These zeros are on the right, but they don't have a visibly drawn decimal point, so there's only 2 sig figs here. Of these 3 numbers I wrote down, 2 is the smallest, so I get 2 in my answer. 1, 2. 4 is trailed by a 1, stays a 4. But I need to keep this in the same place value as it currently is, so I need to fill these other place values as zeros. They're just a placeholder right now. Number 2, if you do 90 divided by 64.678, your calculator will give you 1.3915. Since this is multiplication division rule, I see a non-zero. This 0 does not have a decimal, a visibly drawn decimal, so it doesn't count. There's 1 sig fig. Second number, these are all non-zeros, so there's 5 sig figs. Of these two numbers, which is smaller? Number 1 is smaller, So I can only have one sig fig, one place value in my answer. This rounds to 1, that's it. Then number 3, I have 374.514. Counting these, my 9 and my 7 count, my 0 sandwich, so that makes 3 sig figs. That 0 doesn't have a drawn decimal. And then the 24.218 has 5 sig figs. Of these two, which is smaller? 3. So 1, 2, 3. 4 followed by a 0.51. So this isn't a lone 5, it's a normal 5, round up, equals 375. The math rules for addition and subtraction work a little bit differently, and I would say they're a little more challenging just because we don't use this process as often, and it's not as simple as just counting. It's based on place values. So when you do your math here, you need to look at each of your numbers and say basically which measurement is measured least accurately, which means which has the last sig fig furthest left in relation to that decimal point. So we're going to mark the last place value in each number. So here it's the 6, here's the 5. Those are both the last significant place value. Now in relation to the decimal, which is further to the left, this 5 is in the tenths, which is less accurate than the thousandths. You'd rather have something that can measure here compared to here. So this is your least accurate measurement. That means your answer can only go to the tenths. So the 96.916 that your calculator gives you, measured to the tenths, becomes 96.9. Problem 2, mark your place values. Of these two numbers, which is measured least accurately, the 4 is further left in relationship to the decimal than the 3, so we can report our answer to the hundredths position, which in this case is 16.267. You have a 6 followed by a 7, which is going to turn that 6 into a 7, 16.27. Last problem, mark your last significant place value. The 1 is further to the right, so it's more accurate. This is our least accurate. We can only go to the tenths. Your calculator gives you 16.0611. You have to go to the tenths. A 0 followed by a 6 rounds up. 16.1 is your final answer.